We will now do some exercises. Okay, first one. Let P be the collection of all polynomials in one variable. With real coefficients. Show that P is not complete for any norm. So whatever norm you may put on P, you cannot make it into a complete non-linear space. So solution. So let V be a non-linear space and W a proper subspace. Okay, proper subspace. Then W does not contain any ball of V. Okay, so let, if possible, if not, let BV say 0R be contained in W, because if it contains any ball you can translate it, and therefore you can always have a ball centered at the origin. Okay, then let X belong to V. So then you take R by 2 X by norm X belongs to BV 0R, which is contained in W, which implies that R by 2 X by norm X belongs to W, and this implies that X itself belongs to W. This will imply that V is contained in W, which is a contradiction. Okay, so given any ball, you do not have any proper subspace, it cannot contain a ball. Thus, any closed subspace, closed proper subspace of V is nowhere dense. Now, P equals union n equals 0 to infinity Wn, where Wn is the span of 1x x squared up to n, that is, it is a collection of all polynomials of degree less than or equal to n. Okay, so then Wn is finite dimensional, implies closed and proper subspace of P, and therefore by the bare category theorem P is the countable union of nowhere dense sets. So this implies Wn nowhere dense. Therefore, P is not complete. So this can be extended to any vector space which has a countable basis. A basis means a set of linearly independent elements such that every member of X can be written as a finite linear combination from this set. So if you have a countable basis, then such a space by bare category theorem can never be made into a complete space. Okay. 2. This is a very nice exercise. Let an be a sequence of real numbers such that sigma n equals 1 to infinity an xn is convergent whenever xn is a sequence converging to 0. Show that sigma an is absolutely convergent. So you take an and you multiply it point wise, component wise with a sequence which converges to 0, and that new series, the series which you just get is always supposed to be convergent, and therefore you want to show now that an is absolutely convergent. So solution. So converging to 0 means what? C0 is the space, and you know that C0 star is L1. Okay. So for x in C0, define phi n of x equals sigma I equals 1 to n ai xi. Okay. Then of course phi n is well defined, it is only a finite sum, and now you have mod phi n of x is less than or equal to norm x infinity into sigma mod ai I equals 1 to n. Okay. So this implies that phi n belongs to anyway phi n belongs to C0 star, and you have norm phi n is less than or equal to sigma mod ai I equals 1 to n. Okay. Now if you take x equals sin a1 sin an 0 0 and so on, this belongs to C0, and phi n of x will be in fact sigma mod ai I equals 1 to n, and then norm of x infinity is equal to 1, and therefore this implies that norm phi n is in fact equal to sigma I equals 1 to n mod ai. Okay. Now by hypothesis, phi n of x is convergent for every x in C0, because that is what it says, sigma an xn, these are the partial sums of sigma an xn n equals 1 to infinity, so phi n, and therefore these converge. That is the hypothesis, and therefore by Banach-Steinhaus, norm phi n is less than or equal to C for all n. This implies sigma I equals 1 to n mod ai is less than or equal to C. This implies that sigma I equals 1 to infinity mod ai is less than or equal to C, and therefore ai's are absolutely convergent. Okay. 3. Oh, okay, before that, so try this as an exercise. Let 1 less than p less than infinity an real sequence such that for all x in LP sigma n equals 1 to infinity an xn is convergent. Show that A equals an belongs to L p star, where of course p star is the conjugate exponent. Okay. Same proof you can imitate. So third, so this is application of functional analysis to numerical integration. So A, let n belong to n and let Wnm m from 0 to some Pn be real numbers and let Tnm m equals 0 to Pn be a collection of points in 0, 1. Let f belong to C0, 1, define phi of f equals sigma m equals 0 to Pn, phi n of f, sorry, omega nm f of Tnm. So you are evaluating the function at some points, multiplying it by some weights and add it. Okay, then show that. So call this C01 as V, or not necessary. Okay, show that phi n is a continuous linear functional and norm phi n equals sigma mod omega nm m equals 0 to Pn. Okay, solution. So mod phi n of f from the definition is less than or equal to norm f infinity into sigma m equals 0 to Pn mod Wnm. Okay, so this is trivial, implies phi is a continuous linear, phi n, sorry, continuous linear functional. Okay, and now define f piecewise linear such that f of Tnm equals the sine of Wnm. Okay, so you have 0, 1 here, so you have the points, various points, so Tnm, so this is Tn1, Tnm and so on. So you have various points. So at each point you are taking the sign. So the function takes the value plus 1 or minus 1. So you have plus 1, let's say minus 1 here, minus 1 here, plus 1 here, plus 1 here, minus 1 here and so on. So you have the function which is piecewise linear like this. So this is the function f. Okay, so you fix the values at these points and in between you just join them by means of a straight line segments. Okay, then what is phi n of f? Is precisely sigma mod omega nm m equals 0 to Pn and norm phi n, norm of f is equal to 1 because it takes the maximum values are plus 1 or minus 1 maximum minimum values, and therefore this implies that norm phi n equals sigma m equals 0 to Pn mod omega nm. Okay. B. So now define phi of f equals integral 0 to 1 ft dt. Then phi is also a continuous linear functional. In fact, norm phi is is equal to, in fact, 1 again, because norm phi f mod phi f is less than or equal to norm f infinity into integral 1, and therefore norm phi is less than or equal to 1, and in fact you can show very easily that norm phi is equal to 1. Okay. So show that phi n f converges to phi of f for every f in C01 if and only if 1 phi n fj converges to phi of fj for all j equals 1, 0, 1, 2, etc., and where fj of t is t power j. 2 sup over n sigma m equals 0 to pn mod wnm is finite. They are all bounded. Okay. So as I said, so this is nothing but numerical integration, because we are replacing phi of f, which is the integral of f, by means of a sum which is like phi n of f. Okay, so that is by integration formula, and therefore this gives you the integration, numerical integration. So this is what you do in numerical analysis, and now we are giving a necessary and sufficient condition for the numerical integration scheme to converge. Okay, so solution. So let us assume this way. So phi n f converges to phi of f for all f. So implies phi n f j converges to phi of f j for all j. That is trivial. Okay. And then since phi n f converges to phi of f, so this implies that norm phi n is less than or equal to c, and that is exactly by Banach-Steinhaus, and therefore that is exactly implies 2. Okay, so that is the second condition. Now conversely, let us assume, so conversely assume 1 and 2. Okay. So choose, so let epsilon be positive, a polynomial p such that norm phi minus p, so let f belong to C01. So this is, you can do by Weierstrass theorem. Okay, you can always find a polynomial which does this. Now by 1, since phi n fj converges to phi of fj, that is t power j for every j, that means by linearity we have that phi n of p converges to phi of p. Okay. So choose capital N such that for all n greater or equal to capital N, mod phi n p minus phi p is less than epsilon. Now what does 2 imply? We have that norm phi n is less than or equal to c. Okay. So mod phi nf minus phi f is less than or equal to mod phi nf minus phi n of p plus mod phi n of p minus phi of p plus mod phi of p minus phi of f. Okay. Now that is less than or equal to norm phi n norm f minus p infinity. The second one, so if n is bigger than or equal to n, you have second one is less than epsilon, and the third one is norm phi into norm f minus p infinity. But norm f minus p is less than, so this is less than c times c plus 1 plus norm phi times epsilon, and therefore it goes to 0, and consequently you have shown that that is phi nf converges to phi f for all f in C01. So this tells you, gives you a necessary and sufficient condition for the convergence of a numerical integration scheme, and this comes from the Banach-Steinhaus theorem.